The supernova Betelgeuse is one of the most awaited astronomical events. Betelgeuse is a red supergiant star on its deathbed in the constellation of Orion. Sooner or later, the star will implode, and our skies will be lit with the aftermath of the event even during the daytime for several weeks. However, no one exactly knows when the star will undergo a supernova. There's a probability that Betelgeuse has already imploded, but since it lies about 650 light-years away, the light from that event hasn't reached us yet. Betelgeuse is one of the brightest stars in the night sky, but in late 2019, it mysteriously started dimming. The dimming was so prominent that one could even notice it with naked eyes. The star's brightness continued to decrease for several months, and people wondered if Betelgeuse's end had arrived. However, the red supergiant star returned to its normal brightness after a few months. When astronomers pointed some of the world's most powerful telescopes at it, they were shocked to see what caused the great dimming. So what happened to the star when it was fading before our eyes? Why was this event so catastrophic for Betelgeuse? Finally, and most importantly, why do astronomers want to focus the James Webb Space Telescope on this dying star? Although the star started dimming in December 2019, astronomers noted unusual activity on Betelgeuse when the year began. The images of the star taken in the optical spectrum using the Very Large Telescope showed that Betelgeuse appeared roughly symmetrical, but the photospheric layers showed signs of a huge shock in our line of sight. The photosphere is the star's outer shell from which light is radiated. The researchers also noted that the photosphere had started to expand. It was as if the star was swelling up as seen from the Earth. Betelgeuse continued to swell up at a constant rate of about 8 kilometers a second for most of the year until mid-November 2019, when the outward velocity began to decrease. Assuming this velocity, astronomers believe that within 6 months, the ejected material would have reached a distance of about 10 to 20% of the star's radius above the surface. The outflow stopped by mid-November 2019, and astronomers retook optical images of the star. They were surprised to notice 2 anomalies on Betelgeuse. First, the images revealed a dark southern hemisphere had appeared on the star, creating a dramatic contrast with the previous image obtained on the first day of the year. Second, there was a dip in the surface temperature of the star. It had dropped by about 80 Kelvin. To ensure that the temperature dropped, astronomers used 2 independent methods. First, they observed the infrared spectrum of Betelgeuse just 8 days after taking optical images, and the spectrum confirmed a dip of about 80 Kelvin in the surface temperature. The second method involved analyzing the intensity ratio of 2 spectral lines, vanadium-1 and iron-1. When this ratio increases, the photospheric temperature decreases, a trend that has also been observed on numerous other stars. During the Great Dimming, the ratio increased by a factor of 1.9, indicating a significant temperature drop on the surface of the star. This behavior can be clearly seen in one of the graphs from the team's research paper. This is a spectrum of Betelgeuse with different lines showing different periods. As the Great Dimming progressed, you can notice that the iron-1 line's intensity started weakening as compared to vanadium-1, and because of that, vanadium-1 to iron-1 ratio increases, leading to a decrease in the temperature. The brightness of Betelgeuse reached a historic low between January 27th and February 13th, 2020, about a year after the outflow event began. The star then started brightening again, reaching its normal magnitude after a few months. So what did really happen to Betelgeuse? The researchers note in their paper that this pattern of variation and atmospheric response suggests that an ejection event originated in the photosphere, traveled out through the extended atmosphere, eventually creating molecules and dust as cooler regions of the extended atmosphere were reached. A disturbed local atmosphere, cooler, and of lower density remained. This would be expected when material is suddenly removed from the photosphere, allowing the remaining plasma to expand and cool. So all the evidence suggests that Betelgeuse experienced a massive, never-before-seen surface mass ejection, or SME. Something similar happens on the Sun too, and we call it a coronal mass ejection, or CME. Solar coronal mass ejections result from an impulsive ejection of material, generally from the solar corona to the heliosphere, and this solar process can inform the events observed on Betelgeuse. But the magnitude of the Betelgeuse ejection was nowhere close to what happens on the Sun. That's because the two stars vary in size and evolution stage. By contrast with the Sun, Betelgeuse possesses lower gravity, 1,000 times the Sun's radius, and a lack of high temperatures as found in the solar corona. Betelgeuse ejected 400 billion times more mass than a typical event on other stars or a typical CME. This is multiple times the mass of the Moon, pushed out at incredible speeds. The researchers say that they've never before seen an enormous mass ejection of the surface of a star. It is a new phenomenon that they can directly observe and resolve surface details with Hubble. So we're watching stellar evolution, the aging of a dying star in real time. So the mysterious dimming was caused by a dusty veil shading the star, which in turn was a result of a drop in temperature on Betelgeuse's stellar surface. Astronomers aren't sure what caused the SME or when would such an event happen again, but this event had a severe impact on the star. First, the star lost a considerable mass in one go. An SME of this scale has proved that a dying star can lose significant mass compared to its annual mass loss due to stellar wind. It's like Betelgeuse blew off its top and is now slowly recovering from the injury. The second important thing to note is that the star's 400-day pulsation cycle has mysteriously disappeared after the Great Dimming. Betelgeuse is formally a semi-regular variable star, so it is subject to multiple cycles of increasing and decreasing brightness due to changes in its size and temperature. The red supergiant is known to have two principal periods of light pulsation. The first is 400 days, believed to be due to pulsations in the fundamental mode. The second one is a longer period of about 5.6 years, the origin of which remains unknown. The SME has disrupted the 400-day pulsation period represented by the broken line in the graph from the research paper. After the Great Dimming, the next minimum followed in 189 days, but minima in the following 2 years are separated by about 97 days, 166 days, and 233 days, all values clearly less than the dominant 400 days pulsation period. This variability appears to have resulted from the rearrangement of the photosphere that followed the mass ejection. Astronomers now want to make detailed infrared observations of Betelgeuse using the James Webb Space Telescope. They aim to see the circumstellar region of the south of the star to detect evidence of this mass loss event. The material must have traveled a significant distance in 4 years since the outburst began. Webb's observations of Betelgeuse will provide deeper insights into the physics and evolution of post-main sequence stars. This concludes the 21st episode of the Sunday Discovery series. If you enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so you don't miss any episode of this series.